line integration. So a new concept to you in mathematics is developed in this section. Here, the goal is to try to be able to calculate the energy exerted by a particle that's in motion. This particle in motion obviously has potential energy, well, the potential energy now has been converted into some type of meaningful energy, kinetic or whatever, how you want to call it. So because of that, we can calculate the mass of a wire, say for example, if that's what we're looking at, or we can calculate the work involved as this particle is in motion, this object or whatever it may be. To do that, we look at this concept of line integration. The word line is a misnomer because it's not a straight line, but in the sense of what a line is, or a curve, or here we call it a smooth curve, we want to trace the movement along that path or that curve, and it's been just in the classic sense, this idea of a line integration. You tell somebody to walk in a line, and basically just walk in a straight path. It may be straight or it may be some curvature there, but that's the idea. Let me scroll down so you can see this. We talk about this integration over a smooth curve. Piecewise means that you can break the graph up into different segments. And so here the idea of a smooth curve, is that the partial derivatives exist. Whatever they are, they exist and they are continuous on some closed interval, and then the partial derivatives are not simultaneously equal to zero on the open interval. So there we call the curve smooth. Again, going back to calculus, smooth here means that the derivative is not a spike, or there's no jump in the graph. There's no holes there, right? So here we have the continuity. It's said to be on the closed interval. Now, why the difference between the closed and the open interval? Because the derivative itself may be on the open interval. So the derivative itself may exist at A or at B. So, and so here, obviously continuity on the closed interval, and then the actual derivatives themselves, you don't want them to be simultaneously zero on the open interval. Now, the line integral is this. The line integral is simply evaluating the integral along an arc or a curve. That's the goal. If the function that you're considering is the function equal to 1, then you simply evaluate the arc length from algebra or from calculus 1. Let's see how that function looks like. So here, if f is defined on a region containing a smooth curve of finite length, then the line integral of f along C, or the smooth curve, is given by this integral of fxy, or it could be fxyz, times ds. ds is some change displacement. ds over dt is something familiar. This guy is simply the norm of r prime of t that we called back before the so-called speed. this speed or velocity is seen really as the measurement of the slope, if you will. So if the norm here, the magnitude, I'm measuring so-called length. So the ds is the norm of r prime of t times dt. You recall that here that the norm of r prime of t, if r of t is defined the way we defined it a few chapters ago, we can define it here as x of ti plus y of tj, if it's in the 2 space, if it's in the 3 space, plus z of t k. It's a k. And so if I take its norm, we have the norm of r prime of t is equal to the square root of x prime of t to be squared plus y prime of t to be squared plus z prime of t to be squared. Here for the plane, this ds just becomes the square root of x prime of t to be squared plus y prime of t to be squared, then times dt. Okay, yes, sir. And so what the author has there's just the same thing that we just got through talking about, trying to give a definition to ds. Now, we want to be able to evaluate a line integral as a definite integral, or if we don't have from a to b, then obviously we talk about an indefinite integral. So the line integral of f of x, y, it could be f of x, y, z as well, but f of x, y, ds. Now watch this. If the function f, again, if f is equal to 1, then you don't have this function here, then all you have is the integral of this square root, which is just the arc length. So we want to be able to find this so-called line integral and then make an application to actually talk about what it is. Let's see. So if you're looking for the line integral, and here's the thing, we distinguish between the line integral of f of x, y, ds with respect to the line integral of f dot with dr. They're both the line integral, but they work out a little bit differently. And so this is the first application. So let's see how that works. And you definitely want to get this, so then when you work, we're going to compare this line integral to the line integral over c of f dot dr. Compare that. This is still the line integral as well. So we're going to use this formula. If it's here for the plane, or down below if we talk about the line integral in space. Well, here's the first problem. It says find a parametrization of the path C, and then B, evaluate the line integral of x squared plus y squared ds. So this parametrization is simply, they're saying find R of t. We call this R of t the path by which this function moves along, the path by which x squared plus y squared, again, this is the function, right? So to get the path, we look at the curve, said to be a smooth curve. Here, this is a line segment that's going from 0, 0 to 1, 1. Do you agree with me that this line looks like y equal to x? So this is the line, yes, y equal to x. We need to write y equal x in terms of R of t. No problem. This line segment simply means whatever x is, y is the same thing, right? So you remember that the path is vector is given as R of t is equal to x of t I plus y of t j. So for this particular problem, R of t is simply whatever x is, y is the same. R of t depends on t, right? So we have to eliminate the x and y and to have the parameter t. So this simply means that R of t is equal to ti plus tj. That is, whatever x is, y is the same thing. Well, they're both equal to t. So once you have that, we've got to find r prime of t. This is I plus j. And then we need the norm of r prime of t. Do you agree with me that that's the square root of 2? The square root of 2? Does everybody see that? Donnie, do you see that? This?
Yes, sir.
Okay. Lewis, do you see that? Take the norm of r prime of t. It says those derivatives squared. Well, this is 1, right? And this is 1. This is the square root of 1 squared plus 1 squared. Yes, sir. So that means that t, thank you, t goes from 0 to 1. No, sir. X is equal to t, y is equal to t. So t goes from 0 to 1. So this line integral of this function, x squared plus y squared ds, is equal to the line integral from 0 to 1, x squared, that's t squared, plus y squared, that's t squared, times ds. Again, ds is equal to the norm of r prime of t times dt. Well, we get the norm is the square root of 2 times dt. So this is 2 times the square root of 2 times the integral from 0 to 1 of t squared dt. So we integrate this. This is 2 times the square root of 2 times t to the third over 3. Evaluate that from 0 to 1. Then all we have is 2 times the square root of 2 all over 3. Same old integration. We just got to know where this guy goes and where that guy goes, right? Yeah, that's the very old notation for line integration. in the old textbooks, and I'm old. No, I'm not old, but we had old textbooks back, in the 80s. So um, that notation with that curve was, I think it had started to fade out like in the 50s, 60s, So my professors, that was in their heyday, right? So, so they kept putting that notation there when we were in school. So, yeah. All right, let's look at another. Do you think you can get that one? Let's give you a couple of minutes on it. I think the key to all of these is finding that right path vector, R of t. That's part A, find the parametrization of the path C. So find R of t. It's based on here, the smooth curve. It says it's a line segment from the origin to 2, 4. So R of t is equal to what? T. It's a line segment. You can't square it. That'll be a parabola. 2t. Very good. Right? Because it does say it's a line segment, so you can't use squares and all that type of thing, right? So wouldn't that path, R of t, give us what we want? From 0, 0 to 2, 4. So then little t is the interval between what and what? 0 and 2. Typically, between the first two numbers. This coordinate, 0 and 2. Say that again, I'm sorry. For t, t is based on the x-axis, but you get y because the y term would be 2 times t, right? But t itself goes from 0 to 2. Yes, sir. You still pick that up for y. Exactly. Yes, sir. So this is the interval 0 to 2. So from there, you should be able to get it. John, what you got? You got 40 square root of 5 over 3. And And India agrees with me, so since this is America's a democracy, it's 2 against 1, so we win. No, no. So you found that R prime of t, right? So that guy was I plus 2j, and then you found its norm. Okay. And this guy is the square root of 5. Did everybody get the square root of 5 for that magnitude? Good. Okay, it's the square root of 1 squared plus 2 squared. So ds is that magnitude of r prime of t dt. So that's going to be the square root of 5 dt. So we know we need that. And here we're reading x to equal to t. That comes from up here. And then we're reading y to be 2t. So we have this line integral from 0 to 1. We got that square root of 5 sitting out in the front there. It's just a number. X squared becomes t squared. And then y squared is 2t squared dt. So that becomes 5, the square root of 5, integral from 0 to 1 of t squared. So here, 0 to, is it 1 or 2? What, 0 to 2? Is that Judge, your hand up for? Lou, what's up? Let's see. Sir? Mm-hmm. 0 to 2 comes from up here. That here is based on really this x-axis. X goes from 0 to 2, right? And since here x is equal to t, right? So t goes from 0 to 2. Okay. So this is 5, the square root of 5, t to the third over 3. Evaluate t from 0 to 2. So you get 8 times 5. That's 40 times the square root of 5 all over 3. Yes, ma'am. Why would it be that? If you switch that up, then x would equal to 1/2 t, and then y would equal to t if you did that. Okay. It's just based on the line segment. This line segment goes from 0, 0 to 2, 4. This is based on that. Whatever t is, y is twice that. All right? Yes, ma'am. Yes, sir. The 5 is coming from, this is 1 right here, t squared, and this is 4t squared. 1t squared plus 4t squared is 5t squared. Yes, sir. I just pulled the 5 out in the front. Is that your same question, Jackson? Sorry, guys. He skipped a step. You know, the teachers back in the 8th, 9th grade, you hated them, right? You know, he skipped a step. Don't take his class. Okay, let's move on. I didn't even have coffee, man. I was just daydreaming about coffee when I was walking down the stairs. I ran out of coffee. I had to go to, what's it, health food store? What's that place on South Parkway, food, health something, food, whole good, yeah, that, yeah. These words, man. Whole Foods, yeah. Gotta go there. They got some really good organic coffee, man. Oh, man, it's the best. So, Gatorade, Mountain Dew. I'm gonna need that. We gotta go cut 3 yards today, man. I'm gonna need some Mountain Dew. I talked to one of my deacons at the church last night. We was coming out of Bible study, and he told me, Pastor, don't look for me in Bible study in the summertime. He cuts grass for a living. He cuts 62 or 63 yards. That's what he has. And so, like yesterday, he said they cut 11 yards, and said next week, typically it's like 15 yards, like on a Wednesday. Or I said, man. Huh? I know, man. I know. Some people do. And a guy told me something that disturbed me. He said they charge based on where you live. I don't like that. I think you ought to just charge people based on the yard, you know, and size of the yard. Yeah, man. People are just greedy, you know. I don't like that. And a tree guy told me the same thing. And I know he was right, and I told him that's not fair, because this guy cut this lady's trees where they live, and he charged them $50 to cut the trees down. Charged me $3,600 to cut my tree. I said, that's not right. I said, somebody's going to hell. But anyway, next question. Hello. And just be fair and be right with everybody, man. My goodness. How you go from $50, which I'm like excited about that. He gives me this estimate, but he was based on the other estimates. He was the cheapest of what I've heard, because guys gave me $6,800 and $5,400 to cut our trees. Yeah, man. That's big business. These tree cutting, I tell you. Well, let's look at another. Let me work these, and I want to get through this section and halfway of the other section today before the time gets us. So find the parametrization of the path C, and then evaluate. It's still the same function, but look, the curve is different, or the smooth curve is different. It's counterclockwise around the circle with radius 1, and we're going from 1, 0 to 0, 1. Bless you. So it's moving like this. That's the orientation. Here's how I see it. This is going from t to 0 to t power over 2. Okay. Since it's part of a circle, I'm going to use polar coordinates. And in using the polar coordinates, x, you remember, it's still the same, is equal to r cosine theta. Here, theta would be t. It doesn't matter. You can call it t, or you can call it theta. Then it doesn't matter. I'm going to call it t here. So, yes, sir. If you, on the test, if you use theta, I'm fine with that. It's okay. So r, this is part A, r of t is equal to, here the radius, this little r, that's 1, right? So this is 1 times cosine t, and y is 1 times sine t. So this is cosine ti plus sine tj. This r of t, that position or path vector, is critical to everything, because that's how you build the arc length that's necessary for that integration. It becomes the foundation. If the foundation be destroyed, where shall the righteous be? If our RT is wrong, then, buddy, we're just screwed. You know. So, so r prime of t is negative sine ti plus cosine tj. Its norm is the square root of that negative sine t all to be squared, excuse me, plus cosine t all to be squared. Do you agree with me? That's just one. So this line integral, the t goes from 0 to pi over 2. 0, pi over 2. This is x squared plus y squared. I have to have that x squared plus y squared. That's cosine squared t plus sine squared t. Sir? Oh, t goes from 0 to pi over 2. Oh, x squared is cosine squared, right? And y squared is sine squared. I'm just mimicking. I'm mimicking this right here. I'm just replacing those terms. Replace the x squared with cosine squared t. Replace the y squared with sine squared t. Now I got to replace ds, but ds is equal to the norm of r prime times dt. We got that norm to equal to 1. Right? So here, that norm is 1 times dt. If you were using theta, it'll be cosine squared theta plus sine squared theta d theta. And that's fine. So this is just the line integral from 0 to pi over 2 dt. Do you agree with me? That's just pi over 2. Yes, sir. Pardon me? No, it's still a curve. Yes, sir. Because the terms for x and y are, one is cosine, the other is sine. By doing what? Mm-hmm. There it said as a line segment. This is a part of a circle. Because here, yes, sir. Yeah. Okay. All right. No problemo. All right. This line segment C is given as piecewise. See, it goes from 0, 0, then it jumps to 1, 0, and then it jumps from 1, 0 to 2, 4. So here, find a piecewise smooth parametrization of the path C. So we need two different paths. I need R1 to represent what's happening here, and then R sub 2 to represent what's happening over there. For that first one, let's look at it. You go from 0, 0 to 1, 0. So that guy stays on the x-axis. So here, there's no y input. So for this one, R sub 1, this is equal to, basically, x is equal to x is equal to t. This is just ti. If you want to put 0 times j, and that's just ti. Here, x is equal to t, y is equal to 0. Now for that second part, let's look at its graph. It goes from 1 comma 0 to 2 comma 4. All right. Now for R sub 2, we just resort back to algebra, and we have to determine the equation of the line. If you give me 2 points, I can determine that equation of the line. So, red, no. For R sub 2, we must find the equation of the line that represents the path. Okay. So if we're given 2 points, we can find the slope. Right? I'm given 1 comma 0 and 2 comma 4. This implies that the slope is equal to 4 minus 0 over 2 minus 1. So here, I just get 4 for the slope. I could take the slope with a point, bless you, and use the point slope form to find the equation of the line. So here I have y. I'm going to take the point 1 comma 0, either one, it doesn't matter. So I get y minus 0 is equal to 4 times x minus 1. This implies that y is equal to 4x minus 4. So that means that R sub 2 is here. You see it, x is equal to t, and y is equal to 4t minus 4. And I get it all from this equation here. I just replace the x with t. So here, R of t is equal to ti plus 4t minus 4 in parentheses times j. So for part A, R of t is given, this is what they mean by piecewise. Here we have R sub 1, that was ti on the interval from 0 to 1. And then remember, R sub 2 goes from 1 to 2. And it has the form 4t minus 4 as t goes from 1 to 2. So this is the piecewise smooth parametrization for this problem. So now you need to evaluate the line integral. Here, this part B is at 2x times 3 square root of y. 2x plus 3 square root of y ds. So we first find it based on r sub 1. R sub 1 is ti as t goes from 0 to 1. So this means that x is equal to t and y is equal to 0. So this is the line integral from 0 to 1 of 2t plus 3 times the square root of 0. R prime is equal to I. This implies that the norm of R prime of t is equal to 1. Right? So this is times 1 dt. It's the integral from 0 to 1 of 2t dt. This is t squared evaluated from 0 to 1. We just get 1. That's the first one. So now let's get the second path. R sub 2 is equal to ti plus 4t minus 4j. And this guy is going from 1 to 2, excuse me. So we got to find its norm. So here, this r prime of t is equal to I plus 4j. We find its norm. This is the square root of 1 squared plus 4 squared. We get the square root of 17. Remember, for this one, x is equal to t and y is equal to 4t minus 4. So this line integral that goes from 1 to 2 of this 2x plus 3 times the square root of y ds is equal to the integral from 1 to 2. Here, x is t, so that's 2t plus 3 times the square root of 4t minus 4 times ds. ds is, remember, ds is equal to the norm of r prime of t dt. So that norm gave us the square root of 17 times dt. So we integrate this guy. Let's put that square root of 17 out in the front. This is the integral from 1 to 2, 2t. I'm going to break that up, dt plus 3 times the square root of 17 times the integral from 1 to 2 of the square root of 4t minus 4 dt. Integrate the first guy. This is the square root of 17 t squared. Evaluate that from 1 to 2 plus. For this guy, you have to let u equal to 4t minus 4, right? And that implies that du is equal to 4 dt. So 1/4 du is dt. So you'll know where I'm getting the 1/4 from when I write what I'm going to write now. So we got that 3 square root of 17, and then this is going to be over the 4 at 1/4 there. It's the integral from 1 to 2 of u to the 1/2 du. I'm going to go ahead and evaluate the first part up here as I work. So this is square root of 17 and then times a 4 minus 1 plus 3 times the square root of 17 over 4. We evaluate this u square, that's u to the 3/2 divided by 3/2, and the 4t minus 4 is the one evaluated from 1 to 2. So this is 3 times the square root of 17 plus the 3's cancel out. I have left for 1/2 times the square root of 17, and this is 4t minus 4 to the 3/2. That's evaluated from 1 to 2. So this is 3 times the square root of 17 plus 1/2 the square root of 17 times, let's plug in the t to equal to 2, so I get 8 minus 4 to the 3/2 power, and then minus, evaluate the t at 1, I get 4 minus 4 to the 3/2 power. So that's 3 times the square root of 17 plus 1/2 times the square root of 17. This is 8 minus 4 is 4, and so 4 is 2 to the second, raised to the 3/2, that's 2 to the third, that's just 8. This is 0 there. So we get 3 square root of 17 plus 4 square root of 17. Right? And this was for r sub 2. This is for that second part. So we conclude that that the path, the line integral for both, that first part we got, what did we get? We got 1 for that one. There it is right there. Yep, we got 1 for that guy. This is just 7 times the square root of 17. So we conclude, well, that doesn't look good. Therefore, this is 1 plus 7 times the square root of 17. Yes, sir? Mm-hmm. Talking about this 3 here. This 3 here. Right here. You're asking, why did the 3 do what now again? Yes. This 3 goes with, this 3 is still with the square root of 4t minus 4. It's still there. This is 3 times the square root of y. Y is given to be 4t minus 4. Yeah. I just pulled that square root of 17 out in the front. Yes, sir. Okay. Yeah. No, it's still there. Yep. Okay. Good. Well. All right. So, okay, we got that. So good. Evaluate this line integral along the given path. Again, I need r prime of t, so that's 4i plus 3j, the norm of r prime of t. Do you see that that's directly equal to 5? That's the square root of 4 squared plus 3 squared. You get 5, the square root of 25, right? You see that x is equal to 4t, y is equal to 3t. So this is the line integral from 0 to 1 here of x times y. That's 4t times 3t, then times here ds, which is that magnitude, which is 5 times dt. So this is 60 out in the front, the integral from 0 to 1 of t squared dt. So this is 60 t to the third over 3. Evaluate that from 0 to 1. Just get 20. Any questions so far? Yes, sir. You need to find an R of t that represents that path. How would you do that? Mm-hmm. Because it is complicated for that one. The other ones were easy. Okay, how do you represent? Here's my question to you. If you're going from 1 comma 0 to 2 comma 4, what line segment or line path would you use to represent this? What is x? What is y in terms of t? That's all. Right. That's right. It's not coming from the origin. Exactly. Okay, good. Yes, sir. Yes, sir. The other ones are actually, you're doing that, but since you're coming from the origin, it makes it a whole lot easy. You kind of like just look at it and say, okay, this is x is this and y is that, you know, because the origin helps us out a whole lot, right? Yeah, because you get one of those points is always 0 comma 0. So, but yeah, if you're not coming from the origin, you have to actually find that line segment based on previous algebra. Yeah, and I wanted to do that one here to show you that, so that you just didn't assume always it's always the easy case. It might not be. It might be some more work involved, right? Okay, that's a good one. Let me move on to let's calculate the total mass of a spring. Here, find the total mass of a spring with density rho, the weight density, in the shape of a circular helix, and that's the formula for the helix is always some number times cosine plus some number times sine, and then plus some term over here times k. So we want to calculate the total mass of a spring in the shape of this so-called helix. So all you need to know is what is the so-called formula for the mass. The mass is just what you just got through doing. The mass is equal to here the line integral of some function times ds. That function, we call it some f of xy or f of xyz, but here if that function is given to be density, then you're calculating the mass. Okay? So here they give us rho, they give us the density to be this 1/2 x squared plus y squared plus z squared. Now, can we calculate the mass using what we've just got through talking about from before? Let's see. Well, the good thing is that they give us r, so you know we need to find r prime of t. So this is negative 2 sine t I plus 2 cosine tj plus k. And then we find its norm. So this is the square root of, I'm just going to put the terms in there. This is 4 sine t squared plus 4 cosine t squared plus 1 squared. So it looks like the square root of 5. Yep. So the ds will be the square root of 5 times dt. We're evaluating this integral from 0 to 4 pi. They give us that. So the weight density here is 1/2 x squared plus y squared plus z squared. You see that x is given to be 2 cosine t, and y is 2 sine t, and z is equal to t from the path vector, from r of t. Right? So we need that. So here we calculate the mass, and it's the line integral from 0 to 4 pi. They give us that. This density is 1/2 times x squared, but that becomes, see, the x is 2 cosine t, so just say that's 4 cosine squared t, then plus y squared, that's 4 sine squared t, and then plus z squared, and z is given to be t, so that's just t squared, times ds, that's the square root of 5 times dt. Now we can simplify that since they give us cosine squared plus sine squared. So we can pull the 1/2 out in the front, pull the square root of 5 out in the front, so we have the square root of 5 all over 2 times the integral from 0 to 4 pi. That looks like, what, 4 plus t squared? The cosine squared t plus the sine squared t, factor out the 4, that's just 4 times 1. This is dt. This is square root of 5 over 2. We can integrate now. This is 4t plus t cubed over 3. Evaluate that from 0 to 4 pi. So we have the square root of 5 over 2. We have 4 times t, or 4 times 4 pi, 16 pi, plus 4 pi to the third, all over 3. Evaluate t at 0, you just get 0. So this is the square root of 5 over 2, 16 pi plus 64 pi to the third over 3. You could simplify and factor out of 16 pi, if you will. 16 pi taken out leaves us with 8 pi times the square root of 5. This is 1 plus 4 pi squared over 3. And that becomes calculation for the mass. So the line integral, here's the neat thing about it. The line integral, if the function f is rho, some density, then you're calculating the mass. Watch this. If the function, little f, if it's actually found out to be force, then the line integral comes out to be work. Yeah, that's pretty cool. Any questions here? Well, let's look at that. I want to get to that, but we have to define the line integral in terms of vector notation. It's a definition of the line integral of a vector field. So here the same line integral from before of some f of x, y, z ds can also be understood if I talk about a vector field, some vector field, the dot product of that with dr. And that gives us the same thing. It gives us the line integral. Now this dot is the true dot product. This representation of the line integral using a vector field F as some force times the so-called displacement of the particle that's moving along some path gives us work. That's cool. Now, you remember that r prime of t is equal to dr over dt. If I treat dr and dt as differentials, then dr is equal to r prime of t times dt. And here, that's the dr that we're considering. Right? So for the vector field, we no longer consider ds, because ds is in terms of a function, little f. Let's see how that works out. So here, evaluate the so-called line integral. So I'm given r of t. So do you see that here x, even from the same terminology, x would be 4 cosine t and y is 4 sine t. Is everybody with me on that? From what's given, from the curve, x is equal to 4 cosine t and y is equal to 4 sine t. Okay, right? Also, I need r prime of t. That's negative 4 sine ti plus 4 cosine tj. So this dt, or this dr, is equal to r prime of t times dt. Right? It's negative 4 sine ti plus 4 cosine tj. dt. So I'm going to calculate this line integral. I'm going to calculate this guy now. F dot dr. This is the integral that goes from 0 to pi over 2. They give me that. So f in terms of t is x times y, but that's 4 cosine t times 4 sine t. This is I. Then it's plus y. That's plus 4 sine tj dot product with this r prime of t dt. Right? That's dr. dr is r prime of t dt, which is this negative 4 sine ti plus 4 cosine tj dot dt. So this is the integral from 0 to pi over 2. Let's simplify this. This is 16 cosine t sine t I plus 4 sine tj dot product with negative 4 sine ti plus 4 cosine tj dt. Now let's take the dot product. This is the integral from 0 to power over 2. This is negative 64 cosine t sine square t plus 16 sine t times cosine t. All right. So for both of these, this will be two integrals. Because of the plus sign, you let u equal to sine t. du picks up the cosine t. Sorry about green. I thought I had blue. So this is the integral from 0 to power over 2. This is negative 64, and this is u squared du plus the integral from 0 to power over 2 of 16 u du. So this is negative 64 over 3. That u was sine, so I'm going to put it back there. This is sine cubed t. And that's evaluated from 0 to power over 2 plus 16 u squared divided by 2. So that's just 8 sine squared t. That's evaluated from 0 to power over 2. You evaluate sine at power over 2, you just get 1. So this is negative 64 over 3 plus 8. So what is that, negative 40 over 3? Say it again, I'm sorry. Let's go back and look at the negative work means what? Negative work. Yes, that's something like that. Yes, sir. Let me give you a couple minutes on that one. Let's see if you can compute here this line integral. I got the answer there, so you should come up with that. Try your hand at that one. What does it mean when the work is negative? It's a good question. What does that mean? I may ask that question on the test. That's a good question. It means it's negative. Yeah. Yes, sir. John, did you get 8? Good, good. Anybody else get 8? Got it. Good. This one is not as long as the one that I just got through doing, so. Good, Lewis, you got it? Good, good. Matthew? Good. Jackson? You should end up integrating 9t plus 3. I'm sorry, 10t plus 3. You want to integrate that. So you should, after you take the dot product, you should end up with 10t plus 3. What did you get, Jackson? 14t. All your answers. So what's your integral before that? You took the dot product. So after the dot product, what did you get? Yeah, I wonder.
No, I did. I did divide for. Wait. No, because I did, but I probably messed up the part where
Should be three. Should be 3i plus j for your.
Three I plus J.
There's no square root.
Yeah.
Yeah.
I did not know. I took that because we're doing all other problems. I didn't.
That's for ds, but here it says f times dr, right? So just remember, if it's ds, you need that magnitude, right? If it's dr, you just the dot product of just find if you have given r, find the derivative of r, dot product of that with f.
When we use DR, we're always calculating what
Yes, sir. F dot dr. Yes, sir.
when we're doing DS, it's either with mass or
Just a straightforward line integral. Yes, sir. Yeah, they're all line integrals. It just depends on what you call f. If f is the density, then you calculate the mass. If f is the force, then we're calculating the work. Yep. Yes, sir.
R not 3I, and then the J is 6T plus 1.
No, the derivative for r is 3i plus j. What's the derivative of 2j? It's just 1 times j.
Yeah, but is not I plus the no, it's three. They go separate, right? So then it's 3T plus 1I, right? But then once you take derivative, that's 3. So the TJ, don't you have to multiply that by the 3T plus the 1, making that 3T squared plus T? And then if you take that derivative of that J right there, it would be 6T plus
Yeah.
1.
you got to work
Yeah.
out.
Yeah, let me just work it out because, man, you just went to Neptune. We're gonna keep it simple, okay? Okay. You putting so much in that. You don't separate I and j because they're both given to be one path vector r. So you need to find r prime of t. Isn't that now you can? It seems like what you were doing here. You said this is 3t I plus t times j. I mean that's cool. Take the derivative of that, you get 3i. The derivative of I is just 0 plus j. That's r prime, right?
Wait, so you don't have to, is 3T plus 1 not multiplying by 1 plus TJ?
3t plus 1 is multiplied times I. That's just it. That's all. Nothing more, nothing less.
Even if it was the other way, it's still just not equal to derivative.
So this is the line integral from 0 to 1. The function capital F is xi plus yj, and x is 3t plus 1, excuse me. I, and then plus y is given to be t, dot product with dr, this is 3i plus j dt. Just the integral from 0 to 1. Here we do the dot product, so we get the I components times each other, so that becomes 9t plus 3, and then the j components multiplied to each other, that's just t dt. It's the integral from 0 to 1 of 10t plus 3. That's what I had asked initially. Did you have the integral of 10t plus 3? So this is 10t squared over 2 plus 3t evaluated from 0 to 1. So this is 5 times 1 squared plus 3 times 1. You just get 8. Okay. Um, let's see if I can do two more problems. This next one, let me skip over that one. It works very similar to this. There are two last problems that where you want to compute the work, and I want to definitely work those. Um, okay. So compute the work done by the force field F on a particle moving along the given path. And here, if we're computing the work is given as simply the line integral of F dot dr. So here, F, I need to write out this R of t, but they tell us that x is equal to t, so this is ti plus, and y is equal to t cubed, this is t to the third j. So dr is I plus 3t squared j times dt. So capital F is equal to xi plus 2yj, but x is given to be t, so this is ti plus here 2, y is t to the third j. To give us the graph there. This is the line integral. Here, t is going from 0 to 2. You pick up the 8 because here y is equal to t to the third. So we get those values there. So this is the line integral from 0 to 2. F, capital F, is this ti plus 2t cubed j. Times the dot product for dr, that is I plus 3t squared j dt. If we do the dot product, we get t plus 6t to the fifth dt. So this is t squared over 2 plus t to the 6th. It's evaluated from 0 to 2. So this is 4 over 2 plus 64. Just get 66. Okay. Good. Now let's find the work. If the path is like a circle or a helix or something like that, let's see how that one works out. Any questions here? Do you think you can do that one? That's the last one. There's a bonus question in there at the end, but I don't have time to get to that one. But let's see if you can get this one. Let me give you a couple of minutes on this. Right? And the answer should be given somewhere. Yeah, the answer is negative 10 pi squared. So you're calculating this, right? So you need capital F, you need dr, and dr can be found from r. Take this derivative, and then do the dot product, and let's see what you get. $66. Yep, you got it. Good deal. Brother Newton, you got it? Good. Good. You got it, Matthew? Good, man. Good. Everybody got it? Give you one more minute, then I'll piece something together at 9:55. I had high hopes of finishing this section and getting through half of the next section today, but it's always good to be hopeful. So on Monday, I will cover 15.3 and 15.4 short, so I can cover both of those in one day. So it's up to you if you want your test on Tuesday, or if you just, you could take the test Tuesday, I'm fine with that in class, or I can move on and cover the next bit of information, and I can leave your test in the testing center for you to complete by the end of next week. And I can leave it, you let me know if you want me to leave it in the Huntsville Testing Center or the Decatur Testing Center. It's up to you. So either way, you want your test on Tuesday, or do you want me to leave your test in the testing center? Tuesday will be fine with me if everybody's okay with that. We have it Tuesday in the class. Um, I kind of hate to give it to you outside because I I know you're busy as well and you got things going on. So and I respect that. So I wouldn't want to have you trying to make a special trip, to come outside of the normal class time. So okay, so Tuesday it is. All right, let's look at this problem real quick. See if I can piece it together. R prime of t is -2 sine ti plus 2 cosine tj plus k. So we use that for our dr times dt. And the function f is equal to x, which is 2 cosine ti, plus y, that's 2 sine tj, minus 5z, that's 5t times k. So we end up calculating the integral from 0 to 2 pi of f, which is 2 cosine ti plus 2 sine tj minus 5tk is dot product with -2 sine ti plus 2 cosine tj plus k times dt. Okay. Everybody with me so far on that? Do that dot product, and so we end up with the integral from 0 to 2 pi. That's negative 4 cosine t sine t plus 4 sine t cosine t. That's sweet. They cancel out. Yes. See, that's why Brother Newton was finished real quick, man. He saw that and got rid of that. Woo, daddy. So it's negative 5t. You're just integrating negative 5t. That's all. That's why that guy was so easy. So we get negative 5t squared over 2. Evaluate that from 0 to 2 pi. Negative 5 times 2 pi to be squared all over 2. So that gives us 20, negative 20 over 2. That's just negative 10 pi squared. Well, sounds like some smoked chicken from Big Bob Gibson's. I can smell it. Hadn't had Bob Gibson's in a while, so I'm going to have to go by there and get some good old chicken. The bad thing for me is that you just can't get a quarter piece of chicken. You got to get the half a chicken and eat that with some bread and just call that your lunch. Well, huh? They are good too. Yeah. Maybe that's what I could do. That and the chicken. That may be too much for me.